Welcome, medical data investigators, to a pivotal exploration in our machine learning series. I'm thrilled to be here with you, and today we're diving into a classification task using a well-known data set, a powerful model, and an explainability tool. I'm running this in Google Colab, breaking it down into clear code blocks so you can follow along as we classify breast cancer diagnoses with precision. Let's get started by setting up our environment and gathering our tools for this life-saving mission. I begin by installing the required libraries in Colab with pip3 install interpretLime. These libraries are essential for explainable AI, helping us understand our model's decisions. Next, I import the core dependencies, NumPy for numerical operations, and from Sklearn, I bring in load_breast_cancer to access our dataset, train test split to split our data, random forest classifier for our model, PCA for dimensionality reduction, and pipeline to combine steps. From interpret, I import LimeTabular from the black box module, our tool for local explanations, along with the show function to display results. I set up inline visualizations with setVisualizeProvider and inlineProvider, ensuring our plots render directly in Colab. I also set a random seed with np.random.seed42 for reproducibility. With our toolkit ready, let's load the data and explore its structure. I load the breast cancer Wisconsin dataset using Sklearn's load_breast_cancer function, with return_y equals true and as_frame equals true to get features and target as data frames. The dataset contains 569 samples of breast cancer tumors, with 30 features derived from digitized images of fine needle aspirates, measuring characteristics like mean radius, worst area, and worst symmetry. The target is binary, 0 for malignant, 1 for benign, with 212 malignant and 357 benign cases, making it a binary classification task. The features include mean, error, and worst values for 10 attributes like radius, texture, and concavity, all numeric and without missing values. I split the dataset into training and test sets using train test split, allocating 20% for testing and 80% for training, with random state 42. This gives us 455 training samples and 114 test samples, roughly 43 malignant and 71 benign in the test set, based on the dataset's 37 to 63 split. Let's move on to building our model pipeline. I set up a pipeline to combine dimensionality reduction and classification. First, I initialize PCA, Principal Component Analysis, from Sklearn. PCA is a dimensionality reduction technique that transforms the 30 features into a smaller set of uncorrelated principal components, capturing the most variance in the data. It's useful for reducing noise, speeding up training, and potentially improving model performance by focusing on the most informative directions in the feature space, especially with high-dimensional data like ours. I don't specify the number of components, so PCA will use all components by default, but we could adjust this to reduce dimensions further. Next, I initialize a random forest classifier with random_state42. Random forest classification is an ensemble method that builds multiple decision trees, 100 by default, each trained on a random subset of the data and features. It aggregates their predictions through majority voting to classify outcomes, reducing overfitting and improving accuracy, making it ideal for classification tasks like diagnosing breast cancer, where features may have complex, nonlinear relationships with the target. I create a pipeline with PCA and the random forest, naming it blackbox_model, and call fit on xtrain and ytrain to train the model, letting it learn how transformed features distinguish malignant from benign tumors. With the model trained, I use LimeTabular from Interpret's black box module to explain its predictions. LimeTabular is an explainability tool based on Lime, local interpretable model-agnostic explanations, which provides local explanations for any model. In our case, a black box pipeline of PCA and random forest. It works by perturbing the input data around a specific instance, fitting a simple interpretable model, like linear regression, to approximate the black box model's behavior locally, and then showing how each feature contributes to the prediction. I initialize LimeTabular with blackbox_model.predict_proba to get probability outputs, and xtrain as the background data. I generate a local explanation for the first test sample with lime.explainLocal on xtest.ilog0 and ytest.ilog0, named Lime Local Explanation. I extract the explanation data with local explanation.data 0 and print the details. Predicted 1, benign. True label 1, benign. Correct. Feature contributions show worst area at 0.0670. The strongest positive push toward benign, indicating a larger worst area aligns with benign tumors. Mean area at 0.0267 and mean perimeter at 0.0144 also push toward benign, while worst fractal dimension at -0.0052 and worst symmetry at -0.0044 slightly pull toward malignant. On screen, you're seeing the local explanation plot, a bar chart for this prediction. The worst area bar stretches right in orange at 0.0670, driving the benign prediction. Mean area and mean perimeter, also in orange, add 0.0267 and 0.0144. Worst fractal dimension and worst symmetry, in blue, jut left at -0.0052 and -0.0044, slightly countering the prediction. The final prediction of 1 is marked at the top, a clear breakdown of how features shape this diagnosis. Let's reflect on these outputs. They're a diagnostic blueprint for our model. The local explanation predicted 1 for a true 1, with worst area 0.0670 and mean area 0.0267, pushing toward benign, suggesting larger tumor areas are characteristic of benign cases in this sample. Mean perimeter 0.0144 and worst perimeter 0.0097 also contribute positively, reinforcing the size-related pattern, while worst fractal dimension -0.0052 and worst symmetry -0.0044 slightly favor malignant, possibly indicating minor irregularities. The pipeline's use of PCA likely transformed the 30 features into components that capture key variances, which the random forest then used to classify with high accuracy. Though we didn't evaluate accuracy directly, the correct prediction here is promising. LimeTabular's local explanation provides that XAI clarity, showing how original features contribute to the prediction, even after PCA transformation, making our black box pipeline transparent. To wrap up this medical diagnosis journey, we've analyzed the breast cancer dataset, a 569 sample study of tumor characteristics, and trained a random forest classifier within a PCA pipeline, achieving a correct prediction for our first test sample. The local explanation via LimeTabular revealed worst area and mean area as key drivers for a benign prediction, offering a clear view into our model's reasoning. PCA helped reduce dimensionality. Random forest classification's ensemble approach captured complex tumor patterns, and LimeTabular's Lime-based method provided transparency for our black box pipeline in this binary classification task. Grab this code, experiment with PCA components or other models, and dive deeper into cancer diagnosis. I'm inspired by this health-focused analysis. Hope it's got you thinking about data's role in medicine. See you next time for another impactful data exploration.